So section 4.1 is all about something called related rates. So related rates are these types of problems where you have equations relating two or more quantities of something that change over time, and you're interested in the rate of change. Like how is one of these changing? And the idea is, in most of these problems, you have the information on how one quantity changes, the radius of something. But you want to know, I don't care about the radius of this as much as I care how's the volume changing. If we could figure out a way to connect those two, then we can solve for one using the other. Okay? That's the idea. Right? That's the whole idea. Okay. So there's a whole list of steps here that you can go through. Let's just try some to see. Although the big things I'm going to point out are, well, read the prompt carefully is always big, but draw a diagram. Draw a diagram. Draw a picture. Picture. Okay. So example number 1, and we'll put this down here. And a lot of these are word problems, so it's okay. They're just word problems. Tweety is resting in a birdhouse 24 feet off the ground. Using a 26-foot ladder, which he leaned against the top of the pole holding the birdhouse, Sylvester tries to steal the small yellow bird. Okay. Tweety's bodyguard, Hector the dog, starts pulling the base of the ladder away from the pole at a rate of 2 feet per second. How fast is the ladder falling when it's 10 feet from the ground? So there is a ton of information here, but just start trying to draw it out. So here we go. Here's the birdhouse. Ooh, wow. Boom. What do we know? This is 24 feet, here to here. Okay, what else is happening? Well, there's a 26-foot ladder leaned against the top of the pole. So I'm going to draw the ladder like this. And this is all against the ground. We're just going to assume this is a flat ground. Okay. So here we go. This is 26. All right. What happens next? The next thing that happens is the ladder starts to get pulled. So what do we know? We know that the ladder itself is going to start to move. The ladder is going to move this way, which means that from here, the ladder is also going to move down this way. Okay. So there's definitely change happening here, right? Now go back to what it says. How fast is the ladder falling when the ladder is 10 feet above the ground? We want to understand this arrow at a different point in this picture. So let me actually draw in a second picture here. This is kind of the start diagram. It's often nice to draw a kind of generic start diagram and then to draw another one, right, where you're discussing the exact values that you want to plug into the problem. So, okay. Let's get this again. Now I want to know what's going on when you're 10 feet above the ground. So let's, we don't have to be exact with this, but let's say now we're like this. This is still 26 feet. Okay, this was still your 24 feet all together. Right? And what we're interested in is what's happening here. How is this changing? We still are pulling this way at 2 feet per second. That hasn't changed. What we don't know is how this is changing. Is that changing at the same rate? Is it falling faster? Is it falling slower? I don't know. All I know is that as I pull horizontally, it's the same 2 feet per second. Okay, so we have to start throwing variables in here. So here is kind of like often a first attempt type thing. Anything I see horizontal, I just call X, and anything I see vertical, I just call Y. Here, we'll put that where you can actually see it. Just like get started. If I got a vertical thing and there's no reason to not call it Y, I'll call it Y. If I got a horizontal thing, let me call it X, unless there's some other reason to do that. Okay? Okay. So, what's this? Let's start with this number. So, okay, this is representing change in X somehow, right? I know how to write that down. change in x over time. These problems, as it talks about in the directions above, almost always we're usually thinking time here as what's changing, right? On the bottom. That's going to be 2 feet per second. So awesome, we got some info. Now, what we are looking for is change in y, right? We need dy dt. I don't know. So, okay, I know dx dt, I want to know dy dt. So this is a great point in the problem to be at because I know there are these two quantities changing. I know one of them for sure, the other I don't know. And so once you've got that, then you get to this point where you're like, I need an equation that's going to relate this x and this y somehow. So what way can I relate x and y? What shape here do I see such that I can start thinking of x and y? And maybe it'd be easier to talk about this. Like right now, here is the y, and this we can think of, let me do this in a slightly separate color. This is the y, and then at this specific instance, this full distance is the x. But what you have to think about here is this is changing, right? Look at the two pictures. The y distance, and what am I calling y now? Y is going to be the height of the ladder off the ground. So write that down for yourself. This is important. Write down exactly what you're going to be talking about. Y equals the height of the ladder off the ground. So one thing you'll notice is I kind of was just like, y will be something vertical, x will be something horizontal over here. But I thought more about the problem and realized, oh, you know what? I should be more specific. Y is going to be the height of the ladder. And then x, what's x going to be? X is going to be the horizontal distance from the pole. So this distance x, right? Some number here, and then as the pole slides away, it's going to get bigger and bigger and bigger. We see that right here, though. That's not too bad. We saw that. So let me put some space in here. How do I connect y and x? It's a triangle. Wow, it's just a triangle. So I know how to connect those two. So these are going to be connected by x squared plus y squared, and then equals what is going to be the fixed distance. It's a 26-foot ladder, and that doesn't change. No matter where you slide it, that doesn't change. So perfect. We've got this going. Now I need dx dt, dy dt. And so how is that going to happen? Well, let's think about this. How do I get derivatives in here? Just do the derivative. This is going to remind you hopefully a lot of the implicit differentiation. I'm going to take the derivative with respect to t of both sides. So that's going to end up with x squared, take the derivative with respect to t, y squared equals 0. Now, x is a function of t. The distance here changes as time changes. That implies it's a function of t. So do I know what the function is? No, this is just like implicit differentiation. I don't have any idea what that function is. So there's technically chain rule here. So when I do this derivative, it's going to be 2x dx dt. This is a chain rule just like implicit. This one, again, y is changing, so it's going to be 2y dy dt equals 0. I want dy dt. I know dx dt. So we can plug that in. We have 2x, and then this is 2 feet per second. That's the derivative, plus 2y, and then it's dy dt, which I don't know yet, equals 0. Oops. We don't actually need any of these parentheses. Okay, now I got this x and y in here. What are those going to be? Well, we can think about that. we know what those should be, right? Because we know that y is 10 feet above the ground currently, right? And we can figure out what x is if that's true. So y in this exact scenario at this time is 10 feet. How are we going to find x? Well, just use the triangle. 10, 26, x squared is 26 squared minus 10 squared. X is the positive square root because we're dealing with distance. Okay, so we can plug that into our calculator. Right, 26 squared minus 10 squared. That's going to be 24 feet. Okay, so then give ourselves some more space. So then when I plug this in, I have 2 times 24 feet times 2 feet per second plus 2 times 10 feet times dy dt feet per second equals 0. Solve for dy dt. So dy dt is going to be, so then this is 4 times 24, right? And then we have to just move everything else over. So let's plug some of that in. 4 times 24 is 96. So this will be 96. Okay, so that's feet squared per second over, and then this is going to be 20 feet. So then 96 divided by 20 is 4.8 feet per second. Okay. Now, we have to think about this a little bit. So we messed something up, and this is an actual really good mistake to make. I got this 4.8 feet per second. So, okay, that's how it's changing. But wait, we got to think about this. Isn't it going down? Wasn't this 24 feet? And then a few seconds later, it's now down to 10 feet and is moving down. 24 to 10, that sounds like it's going down. That's a negative slope. So these can get a little tricky, but it's often good to stop and think. This should be a negative. Why? Because to solve for this, I had to subtract over. But the real why of it is this is decreasing. It was at 26 feet and it's sliding down. That's a decrease in y. So be careful with that. That's a very common thing to mess up, is to not have the right sign on your rate of change. But there you go. It's a lot. It's a big problem. There's a lot going on here. Draw your picture, try to label things, connect your variables, do a derivative, and then plug in your knowns. Solve for the one you don't know. So let's try another one. A baseball diamond is a 90 feet square, 90 foot square. That's a good question. In any case, baseball diamond. We can draw this. Boom, boom, boom. Okay, we got our baseball diamond. A player runs from first base to second base. So this is first base, this is second base, and the person's running. Look at me go. Woohoo! Okay, I'm running that way. And we know that they run at 25 feet per second. So there's your derivative we're going to need. How fast is the player moving away from home plate when he is 30 feet from first base? So home. Okay. So we've got a couple different changes here, right? And it's a little tough to see. So we're going to redraw this, right? So that we can kind of, see what's going on here a little bit better. So we've got home is here. Here's first base, okay? And I'm going to draw the runner some decent distance away. And this is a line going here to second. Okay? And, we can actually just draw these lines like this. Now, if you're a baseball person, you might be like, well, that's not exactly how the bases are set up, but we're pretending the bases are at the corners of the square, just to make life easier. Okay, I know this is 90 feet. this is 90 feet. And so I have what? I have a distance moving this way from 1 to 2. But look, I also have this distance here that I'm trying to learn about. And what I need you to imagine is as this person moves, this dotted line follows, and so that distance will be increasing. That's what we want. We want to know how that distance is increasing. Okay? So what you end up having, and maybe we can draw some nice pictures here for this, is you start here at home. All right, you draw over to first base, and when the person first starts, right, we've got this little triangle. Again, a triangle. Then sometime later, you've got home plate, first base, and they're a little bit further away. Okay, here they are, still running that way. That way. And it's going to keep going, right? It's going to keep going. They're going to keep running until second base, towards second base, and this distance here will grow. So what do we need to do? We should label these things. The distance, and I'll zoom in on this picture here, and we can work off of this one. And you call these whatever you want. It doesn't matter. You just got to pick something and stick with it. We're going to call this distance little h. It's the distance from home base to the person. And we will call the distance from first to the person whatever you want. We'll just call it x, because why not? Not creative. So what are we interested in? We're interested in learning about dh dt. What's this? What do we know? Well, we know that their distance from first to the person is increasing, and specifically, we know, they told us, it was 25 feet per second. Okay, so what's the connection here? Well, again, this is just a triangle, and this is a fixed 90, right? So it might be a little tough to see, but this is the right angle here. So what we have altogether is h squared is equal to 90 squared plus x squared. This distance squared plus this one squared will be h squared. Okay, so we've got a formula, relates our variables. We've written down what the derivatives that we need are, so we can do this. Do the derivative with respect to t on both sides. d dt of 90 squared plus d dt of x squared. Okay, again, 2h dh dt. This is 0. 2x dx dt. And hopefully you're seeing the pattern here, right? These are all very similar. Okay, so then I want dh dt. So what can I do? Well, I can drop this over here, divide it over, and then I just start plugging in what I know. So 2x, so I've got to find x. dx dt is 25 feet per second, so this is 2x times 25 feet per second, okay, over 2 times h. So what I need to do is find out at this exact moment, what are these distances? So what moment? Well, we wanted to know what's happening when this person is 30 feet from first base. That's x, right? So in our problem here, x equals 30. Okay, so then what's h going to be? Well, we can figure that out. H squared is 90 squared plus 30 squared. So we'll just take the positive square root of that. So we can type that in. So that's going to be square root of 90 squared plus 30 squared. And that gives me, and again, square root, 94.87. That's rounded. So we're going to round it 2 decimal places there, feet. Okay, so then just plug in. So then dh dt is going to be equal to 2 times 30 feet times 25 feet per second over 2 times, and then we have this 94.87 feet. And there you go, right? We got this. We can do this together. So we've got 2 times 30 times 25 divided by 2 times 94.87, and this is dH dt is 7.9. And again, this is rounded. And that's feet per second. Just do a quick double check with this. This is a positive change, rate of change. So that's saying that the distance h should be increasing. Let's look at our picture, right? Whoop, too far. As time goes, h is going to be increasing. As this person moves closer to this base, this dotted line that we kept drawing will be getting bigger and bigger and bigger. There you go. All right, let's try this next one. We're going to go down here and give ourselves a bunch of room. The Monticello High School swimming pool is an inverted cone. That's weird, but okay. With height 20 meters and radius 5 meters. I don't know why that would be the case, but okay. Here's our cone, our swimming pool. So it's got a height of 20 meters and a radius here of 5 meters. Okay. It is being filled with a hose which pumps water in at a rate of 3 cubic meters per minute. Okay, so we've got a hose. Here's our hose. It's all wrapped up here, and then it goes and it's filling in the water. Okay. So then that rate it's filling in is 3 cubic meters per minute. Okay. Filling up. So right here, filling with water. What a picture. When the water level is 2 meters, how fast is the water level rising? Okay. So we've got water level as something, and then we also have this cone and its volume. So we're definitely going to need the volume of a cone, because that's what we're doing. We're filling it up. So the volume of a cone is going to be definitely necessary. So the volume of a cone is pi r squared height over 3. Okay, so I've got this v, we've got this r, we've got this h. All right, so we got to think about this. Volume is changing. Good. Height of the water is changing. Okay. I'm not sure maybe exactly right now how to, maybe I don't know how to exactly connect it to this picture yet, but okay, height is definitely changing in some way. Like height of what? We got to think about that, but that's okay. We'll figure that out. And then the radius, that's also changing. It's not changing for the full big cone, but depending on the water level, it's going to change. So we need to draw out some variables here for ourselves, okay? So r is going to be the radius, right, of the cone filled with water. So what do I mean by that? I know that this water is sitting in this big cone, but we are going to specifically only consider r to be the radius of the cone, that's the piece of the cone that's filled with the water. So maybe we should draw out this cone bigger so that you can see exactly what I'm talking about here. So I've got this big swimming pool. Here it is. Whoops. Hopefully that's not what the swimming pool looks like. Oh my god, I don't want to do another one of these. Three, two, one. So let's draw the picture again, just time bigger, so we can get a better idea of exactly how we want to measure these things. Okay, go down here. Okay, so let's draw some water in here, right? Because this is part of the reason that we're here. We're filling this up with water. Okay, there's our water. All right, and I guess water here too. Okay, so what is R specifically? R is going to not be 5, it's going to be the radius at this point. So once we fill it up with some water, if you just stop for a second and think about what's in there, that is a smaller cone inside. That's R. And the H that we actually want to consider is this height. Not the total height of the cone, but the height of the water cone. So there's a big cone structure, right, that's empty to start, and then as we fill up, that fills up evenly throughout so that there's a water cone in blue there. Okay, so H is the height of the water. All right. So then what we have here, again, 3 things, right? We've got the volume V of the water cone. So maybe we should write that. V is the volume of the water. Again, it's a cone, though. So that's changing. As I fill up more, the height's changing. As I fill up more, the radius is changing. So we already found the formula. V equals, let's go get it, pi r squared h over 3. So we have this problem where we're filling the tank. We've got everything labeled. We've got a formula connecting. But there are too many variables in here and not enough information given for us to just deal with this function. And so we have to use a little trick here. And the trick is that the relationship between R and H is very similar no matter what height tank you have. And so this is maybe a little bit weird, but let me draw a little extra piece of this picture. And then I'll draw a second picture to hopefully help you see what's going on. So pretend the water was all the way up at the top. I'm going to have this radius and this height. Now the water's down here. I have this radius and this height. If you draw that picture out separately, just the radii and height, you're going to end up with something that looks like this. Okay, that's the big one. And then you'll end up with this separate one where maybe the height is here. This is the blue is the liquid. And what you end up getting is a similar triangle, R and H. So this R is the overall big, which for us was 5. The height was, again, the overall big, which was 20 meters. It's 20 equals 5. And so because it's similar triangles, this little triangle to the big thing, right, what we end up knowing is that the ratio of the radius and the height is the same for both triangles. So let's quickly just do a little r prime here, and then this little height. So that's that little blue one, and then just this piece is a little h prime. So these are the smaller radius and height when you have only filled up the tank a little bit. And so similar triangles means that we can do, and we have a choice here, we just kind of have to think about which one would be better. We could do r over h is equal to 5 over 20, which is 1/4. This will be true for any triangle here, any r prime, h prime, anything like that will also be 1/4. Right, so that's 5 over 20. Or h over r is going to be 4. Any h prime or r prime, no matter where I filled this tank up to, if I measure the radius and the height, this will be how they're connected. So this is a little trick using similar triangles. So okay, all right, well, how does that help me? Well, this helps me try to get rid of one of the variables. Basically, I've got this r squared and this h squared in here, and I can get rid of one of the variables using whichever one of these I want. So how do you know which one? Well, just take them and solve for a variable. So r equals 1/4 h is an option, or I can use h equals 4r. And going through here, well, we got to go back and say, which one did we actually want and which one were we given? Because that might also determine things. So let's see. When the water level is 2 meters, how fast is the level rising? So we actually want dH dt. So dH dt, this is what we want. Okay. We know what? Which change do we know? Oh, we're filling. So we know dV dt. Okay. So this is the one we know. So we want this one, we know this one, which means there's no room for having r anymore, right? I don't know how the radius is changing, so that can't be in my formula when I try to do the derivative. So I'm going to have to use this one, substitute out the r. So the way that's going to work is I'm going to take this formula and the volume and put them together. This will be pi 1/4 h squared, so that goes in for the radius, h over 3. Okay, that's going to be the volume equals pi. I'm going to get 1/16 h squared times h over 3. But I can combine these. This is volume equals pi, and then 16 times 3, 48. So that would be h cubed over 48. Okay, and then now I can just do this like I did the previous problems. Do the derivative of each side. So then I'll take the pi out, take the derivative, and I can take the 48 out. H cubed. Okay. Now, this is just dV dt, so that's not too bad. Over here, remember, h is a function of t. The height is changing as time changes. So this technically needs chain rule. Right, drop the 3. And then it's going to be h squared dH dt. Okay. We could simplify. This is going to be dV dt equals pi over 16 h squared dH dt. Right. So we're going to have to go into a new page here. And again, we wanted dH dt, so let's solve for that. dH dt equals, and then we've got what? dV dt. We're going to divide this over 16 over pi, and then we're going to take this and divide this over. Okay, and so we know these things, right? Let's go back to the original problem and see what things we knew. We know that the volume is changing at 3 cubic meters per minute, and it's an increase, so positive. And we know that the level of the water is 2 meters. So let's plug that in. That's going to be 3, 16 over pi, 1 over 2. And that's 2 meters squared. And this one is cubic meters, I believe, per minute. Per minute. Okay? And so then at this point we just plug in. And so you can use, the first thing we can do is just try to keep pi, right? So 3 times 16 divided by 4, because don't forget it's 2 squared. So that's 12 over pi, right? And that 3 meters, 2 meters, meters per minute. Or, if we want to know, like, okay, well, what is that kind of close to? That's about 3.82 meters per minute. There you go. So the change in height will be 3.82-ish meters per minute. Okay. So there you go. Hopefully that's not too bad. This trick is really tough. This is something that is definitely tricky, but isn't too bad, I think, once you see it. So you've seen one where we didn't use a triangle. You saw a couple examples where we did use triangles, which is very common. But the steps are all very similar. Draw yourself a picture, get variables on all the different quantities, relate them with an equation, take the derivative, solve for the derivative you want, plug in everything else, but you got to plug in everything else after you've taken the derivative. That's important. And then do a little bit of algebra. So practice some of those problems up. Hopefully they're not too bad. If you have any questions, let me know, and I'll see you in the next video.